Okay, welcome back. Discrete optimization, knapsack. So I want to go back to the branch and bound and talk a little bit about strategies. I put something under the rug, and I want to cover them during this lecture. And you're going to see some of these things are going to be very interesting later on. Okay, but you need to understand them. It's going to build on branch and bound, but just refine the kinds of things, actually expand the kinds of things that you can do in branch and bound. Okay, remember branch and bound. We are working with real artifacts that we can break, but still we are using the linear relaxation in general, or a relaxation in general, to actually compute good, optimistic estimates of the best you can do. Okay. So once again, the key idea between branch and bound is that you look at this exhaustive search, and you want only to explore a very tiny pieces of this tree. Okay. And you do that with this basic, relaxation idea. Okay. Now, one of the things that I didn't talk about last time is that you can search that tree in many different ways. So we saw depth first, branch and bound, and I will talk a little bit about it again, such that to refresh your memory. But there are other things that you can do, and some of them are called best search, best first search, or limited discrepancy search, and that's what I want to cover today. Okay, I want to give you an idea that there is one thing that you need to consider when you solve a problem. It's also how you explore that particular tree. There are many others, and you'll see more in this class. Okay, but at this point, I just want to give you some of the ideas on what you can do and compare them. Okay, so depth first search, you explore that's what we saw last time. You explore your tree in a depth first fashion, and you prune the search tree as soon as you come back to a node, and that node is an optimistic evaluation which is worse than the best solutions you have found. Okay, that's depth first search. Okay, now we're going to see best first search, and the key idea there is that you want to select at any stage the node which has the best evaluation. Okay, so that's what best first search is, and we'll see limited discrepancy search, where what you will do is trusting a greedy heuristic, and you'll be following this heuristic and then allowing you to move away from the heuristic in a very systematic fashion. So I'll go into the details of these two things. Okay, so I just want to remind you of depth first search first. Okay, and we are using the linear relaxation here for the knapsack problem. Okay, and remember what we did was basically exploring this tree. We would find a good solution there with a cost of 8t, and then we would go back to the other part of the tree here, where we don't select the first item, and you see that the optimistic evaluation here is worse than the best solution that we have found, and therefore you can prune this entire tree. Okay, so that's what I told you before. In depth first search, when you have an optimistic evaluation of a node, you compare it to the best solutions that you have found so far, and if it's worse, then you just throw the entire subtree away. Okay, so that's what depth first search is about. Okay, so in a sense, the key idea for depth first search is like in the NFL, you want to go deep, okay, and try to find good solutions quickly. Okay, when does it prune? It prunes as soon as you reach a node whose evaluation is worse than the best found solution. Okay, and one of the questions that I have for you is how efficient is it from a memory standpoint? Okay, and I'm going to always ask you questions like this during this class. Okay, and the key idea when you want to answer them is you have to exaggerate. Okay, so just assume extreme cases and try to see how these things are working. Okay, so how much space is a depth first branch and bound going to take? Okay, can you find the answer to that? Well, it's very simple, right? So you always go left, 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 left until you get stuck, okay? So essentially the number of nodes that you can accumulate in memory at any one time is essentially the length of that particular branch, which in this particular case is the number of items that you can put in the knapsack. So yes, it's actually pretty memory efficient because you look at every one of the items, and you have to do that because you have to find out whether you select them or not. And that's what you select inside a particular branch. Once you have, explored that branch, you can remove some of these nodes and you will select other ones by taking the other branches, but you always have essentially one branch at any one time. Okay, so let's look at the next technique, which is best for branch and bound. And to illustrate this, I'm going to use a very, very simple relaxation, the one where we remove the capacity constraint, because that allows me to illustrate the concepts in a better fashion. Same ratio of values and weight and that before, same capacity for the knapsack. Okay, and once again, all the nodes have the values that I've accumulated, the space left in the knapsack, and the optimistic evaluation. Okay, so initially best first search, look at a particular item, and then generate two subproblems. Okay, whether you select the item or whether you don't select the item. okay? And now depth first search, or best first search, is going to look at all the nodes which are there, okay, and select the one, okay, which is not close, which means we haven't explored, it's children yet, okay, which has the best evaluation. And in this particular case, we take the one where we selected the item, and which has value of 128, right? And we basically explore it, generate these two children, okay? One of them is infeasible, and the other one is a value 80, okay? And now we are basically have to consider these three nodes, one of which is infeasible, so we have essentially to consider these two, and we take the one which has the best evaluation, which is this one, okay? We expand the children again, okay? And what we get now is these three nodes, okay, which have a value 80, 83, and then 35. And once again, we take the one which has the best evaluation, 83, okay, and we expand it. And we get our first feasible solution there, which has a pretty bad value of 48 and an infeasible solution, okay? So at that point, once again, we will be basically evaluating, taking the best node, the node which has the best evaluation for expansion, okay? So this node we already know, but I'll come back to that in a moment. We already know that we will never select it, right? Because it's worse than the best solution that we have. But we expand this one, and we find two solutions, one with value 80 and one with value 45. Okay, and this is the best solution that we have. At this point, we look at the best node which is not expanded inside a tree. We see this guy, but you see this guy doesn't have to be expanded because it's already worse than the best solution we have found so far. So we can stop the exploration at that point. Okay, so that's best first search. Okay, you always look at the node which has the best optimistic evaluation. That's the one that you select. You expand, its children, and then you repeat the process. Select the one which has the best evaluation and keep doing this. Okay, so in a sense, best first search is greedy, right? Always go for the best, okay, and expand that one. Okay, most of the time when you expand that particular node, their value may go up, and therefore they may go down, and therefore you don't select them anymore. Okay. When is best first search pruning? It's essentially pruning when you try all the nodes that you can expand have a value which is worse than the best solutions that you have found so far. At that point, you have all these nodes which are floating around. They've not been expanded, okay, but it makes no sense to actually explore any of them, so you stop. And that's when the computation stops. Now, is it memory efficient? Think about it. Okay, once again, exaggerate. Okay, how would we be exaggerating in this particular problem? Okay, well, we can be just silly, right? Suppose that the optimistic evaluation is going to be amazingly optimistic. It's going to give you plus infinity all the time. So if you do that, how much space are you going to use in best first branch and bound? Think about it. Okay, essentially what you're going to do is take a node, they have all the same value, infinity, you're going to expand one, okay, and then you're going to expand the other one and so on, and you will have to expand all of them. So you're going to store the entire tree inside memory, which is kind of a disaster, right? Because not only you will take exponential time, but you will also take exponential space, and space is actually one of the main limits in computers these days, okay? So, this is the worst case for best first branch and bound. Now you may ask, when is best first branch and bound really good? Okay, and once again, exaggerate, right? And we can do the exact opposite exaggeration, right? So you have the perfect evaluation, okay? If you have the perfect evaluation, okay, then you will select the minimal number of nodes, okay? So you see a little bit, what is important in the best first branch and bound. If the relaxation is really good, then the number of nodes that you will explore will be very small. Otherwise, you will explore a large number of nodes, and these nodes are inside memory. Okay? Now, let me talk about the last search technique that I want to talk about today, which is limited discrepancy search. It's actually a very interesting and amazing search strategy. And it assumes that you have a good heuristic. Okay? Assume that you have a greedy algorithm which is really good. Okay? And that it makes very few mistakes. Okay? That's what you assume. The heuristic is making very few mistakes. We assume that the search tree is binary, okay? And following the heuristic means always going left, 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 right? So you select the item, you select the item, you select the item, okay? And branching right means the heuristic is making a mistake, okay? So if you do this, okay, this is what, limited discrepancy search does, okay? It wants to avoid mistake at all costs, okay? So we basically explore the search space by increasing number of mistakes. We first explore something which has, 0 mistakes, then 1 mistake and 2 mistakes, okay? And what we are doing there is really trusting the heuristic less and less. Okay? We start by trusting the heuristic, trying to avoid mistakes, and then we allow a certain number of mistakes, and then more and more mistakes until we don't trust the heuristic. Okay? So in a sense, the way to view this is that limited discrepancy search can be viewed as a technique which is basically exploring the search, this entire tree, through a bunch of waves. The first waves assume that you make no mistake. The next wave, wave number 1, assume that you can make one mistake, and then wave number 2, 2 mistakes, and so on and so forth. Okay? So let me show you that on the exhaustive tree. Okay? So you start at the root, obviously, and then you assume that you make no mistake. You follow the heuristic all the time. That means what? Branching left, left, left. Okay? And that's what you see there. This is, the first wave that you see there. Okay? Now the second wave is going to allow you from one mistake. Okay? So that basically means that you can only branch once on the right. Okay? So for instance, you can go here. Okay, but then you will have to go left, 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 left. Okay, and this is what you see in the first wave. Okay, you go left, you go right, and then left, 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 or you go left and then one right and then only left, or left, left, and then one right over there, right? So this is what you explore in the second wave. And there is something which is really interesting here, right? So this is half of the search space. This is the second half of the search space. And what you can see here is already in the second wave, you are already exploring one particular configuration, which is in the second half of the search space, which depth first search would never do until it has explored the entire first half of the search space, right? And this is one of the interesting things about limited discrepancy search. It actually probes the search space in many different places. Okay? Then the third wave is going to be making 2 mistakes. That means that you can take 2 rights and 1 left. Okay? And that's what you see there. And at that point, we have almost explored everything. Okay? And then essentially the last wave is going to explore these guys on the left. Okay? So let me show you this example of the knapsack example as well. Okay? So we start from the configuration. Okay? In wave 1, we start from the root and we branch left only. Boom, boom, boom. And in this particular case, it's kind of annoying because you get into infeasibility very quickly. Okay? The first wave, okay, is basically you can do 1 right, and this is what you get. Okay? And so you basically make 1 right there. You make a mistake with respect to the heuristic. You let the heuristic make a mistake, and then you go left, or you go right there and go left again. And at that particular point, you find the optimal solution already. Okay. And then in wave 3, you explore 2 mistakes for everyone, and most of these things are going to be rejected, of course, because we have already the optimal solution there. Okay. So limited discrepancy search. In summary, trust the greedy heuristic. When does it prune? Think about it. When does it prune? Well, it's exactly like in-depth first search. When you see a node, okay, it has an evaluation which is worse than the best found solution so far. You know that you don't have to explore it, so it prunes like in best first search. And no, here is an interesting question. Okay, is it memory efficient? Okay, so compared to depth first and best first search, is it memory efficient? Okay, now this is a very interesting question. You know why? Because I haven't told you really how to implement this, okay? And depending upon the way you will implement this search, okay, there will be an interesting trade-off between space and time, okay? You can implement it very efficiently, but it will take a lot of space, or you can implement it by doing redundant work, and it will take minimal space. So the implementation can be between the best first and the depth first search approach, okay? So think about it and think how you would do this. This is a very interesting topic. Now, limited discrepancy search, there's some beautiful application in scheduling. We'll come back to that in routing as well. So it's a very interesting technique when you have a good heuristic, when you know what you're doing. Okay, so let me conclude here. So we have seen search strategies here, and we have talked last time about relaxation. Okay, the big idea last time was relaxation. The big idea today is search. Okay, now how do you choose between them? Okay, this is a very interesting topic in optimization. This is one of the most important topics. You can find really strong relaxation, but they will be so slow that you will explore a very small tree, but it takes a long time. Or you can have a relaxation which is really strong, decrease and really fast to compute, and decrease the size of your search space substantially. So you have to find, the right relaxation and the right part of the search tree that you will explore. This is a very interesting topic. Okay, most of this is going to be problem specific, like everything in optimization. Okay, and finally, there are many other strategies, and I really encourage you to actually think outside the box and think if you can find all the kind of strategies that are going to be good. Okay, think about it. Okay, so at this point, this is very interesting. We have covered the knapsack problem entirely. Okay, it's time for you to start the assignments. Okay, and we'll go into more sophisticated techniques in the next couple of lectures. Thank you very much, guys. Okay, so it's time to go to work and actually solve these assignments. Bye.